but for now the most important task at hand is to introduce the notion of redundancy. This is a very important concept. It is a very important concept in engineering, very important concept in communications. Now error control coding is considered a form of redundancy. Can you explain to me what type of redundancy you are introducing in error control coding? It is a form of redundancy, do you agree? Yes, what is the redundancy you are transmitting some additional bits so that the information bits can be protected. Okay. So here is so redundancy can come in different ways, and here is where I want you to sort of think of redundancy in a multi-rate context, and today we will be talking about this multiple times, and we will come back and look at it and visualize it again. But let me just sort of give you a flavor for what the element that we are trying to introduce here. Now redundancy in this notion, supposing I had a signal spectrum which went from minus pi to pi, okay, and if I upsampled by a factor of m, I know that we know that you will get a signal of the form which is contained between minus pi over m to pi over m, and there will be many copies of this signal. Okay, so this is copy number 1, copy 0, this is copy number 1, this is copy number m minus 1. Okay, and the limits would be minus pi over m to pi over m. That is what they would be, and if there were m signals, this would be the conventional transmultiplexer, where you could think of one signal, another signal, a third signal, and so on. Okay, so that would be the way that you would achieve. So if you used the upsampling by a factor of m and we combined it with m signals, then this is what we would get. Okay, there is no gaps in the spectrum. So basically you use the information or the resources optimally. Now very important answer, think about this question. I have only m signals, but I want to introduce this notion. I want to upsample by n, where n is greater than m. N is greater than m. Okay, what am I trying to do? I have only m signals. So which means that my spectrum will now be not pi over m, it will be pi over n. Right, and it will be narrower, pi over n. So which means that every one of these representations, okay, can actually be visualized as narrower than the band. So in other words, I have separated out the signal, at least conceptually. Okay, because when I upsample by a factor of n, I have made the spectrum more compact, but I have only m signals. So potentially in the total bandwidth of 2 pi, I will have some gaps. Okay, so I want you to start thinking along those lines. So now what have we done in the same spectrum 2 pi? I have now fitted m signals, but because I upsample by a factor of m, I am able to create some gaps in the spectrum. Okay, so the notion of redundancy in our context, so there is the notion of redundancy, that means some additional resources so that we can process our desired signal in a more efficient manner. So redundancy. So in our case, the redundancy is coming by upsampling by a factor of n, where n is larger than m. But where did I use more resources? It is still sitting between 0 and 2 pi. Where did I use more resources? It is a higher sampling frequency, sample rate is higher, that means bandwidth was higher. Yes, 2 pi is the discrete time frequency, but actually it represents. So in other words, we have effectively used wider bandwidth, which means that effectively for m's, if only m channels had to be transmitted, we can create guard bands. Okay. So, we find that the notion of redundancy was what multi-carrier modulation was using, and we now say that okay, yeah, now I can think of it as where do I allow more resources, I have to allow more bandwidth. Where is the bandwidth going to come in if I increase the sampling rate more than I need to. Okay. So, in other words, the when I have m signals and I upsample by a factor of m, then the FDM signal. So, in this case the FDM signal, frequency division multiplex signal, this is has the minimum sampling rate that is required. So, basically it is the output signal is running at m times the input sampling rate. So, that is at without any redundancy, but in this case what we are seeing is it is going to run at n times the input sampling rate, which basically means that I am going to utilize more resources, and therefore the notion. So, now how do we create these gaps, how do we operate it? This is a conceptual presenting the concept, but now the key challenge is how do we build this and leverage it for as we move forward. Okay. So, if you are comfortable with this, then we want to quickly take this particular thought process forward. So, the first step in a multi-carrier modulation will be, yes?
There we had n copies, right?
Yeah.
So, where are we gaining them?
I am sorry? So, if you think of it that I will throw away n minus 1 copies after the upsampling. If you see that in the first case when I upsample by m, I have m minus 1 copy which I throw away m minus 1, I keep 1, throw away m minus 1, and likewise each of those gaps that were created is filled in by another signal with the same amount of bandwidth. Now, what we are doing is we have only m signals. So, in other words, if I divide the original signal as per the bandwidth 2 pi over m, I have to fit in one copy, but that one has been more compressed. In the next channel I want to fit in one more. So, like I said, the center frequencies and other things are this is more to just start you thinking as to where the redundancy comes in. So, in other words, in a multi-rate system, the minute I upsample by a factor n which is larger than m, somewhere redundancy has crept in. So, I just want you to, and one way that you could visualize the redundancy is like this, but this is not exactly the way we will exploit redundancy. In fact, that is what a significant part of today's lecture is actually going to be the understanding of redundancy and the implementation of redundancy. Okay. So, basically the upsampling by a factor of n gives you room for adding n signals, but you are only going to keep m signals, which is m is less than n. So, therefore, there is potential for gaps. Okay. So, the first step in a multi-carrier system is the synthesis filter bank, the step of synthesis. Okay. So, synthesis filter bank basically says I have m signals upsampled by a factor of m. This is a traditional way to do that. Pass through a filter f naught of z and add it together. So, this would be s naught of n. Okay. The second channel s1 of n upsampled by a factor of m, pass through another filter f1 of z, similarly all the m minus 1 signals. Upsampled by m, s of m minus 1 of n, f of m minus 1 of z. Okay. So, this is the conventional way that you would combine in a transmultiplexer type structure, this is what we would do. But the first thing that we are going to say is, okay, this is not m anymore, it is n, upsampled by a factor of n, where n is greater than m. So that is our intent as far as the redundancy part is concerned. Okay. Now, the way we represent typically a synthesis stage is as follows, because we want to combine it to produce a single output. So, the way this is represented is, you write it as a row vector f0 of z, f1 of z, fm minus 1 of z, and then a column vector which is the inputs which will get combined. In this case it will be S naught, let me just write it in the context of the upsampled by a factor of n. This will be S naught z power n, S1 z power n, and the last one would be Zm minus 1 z power n. Okay. Now, if I want to do any optimal implementation of the upsampling, I should use the noble identities, and the noble identities require me to split it into polyphase components which are dependent on the upsampling factor. So, which means that now when I write the polyphase component matrix, I have to write it with n polyphase components and not m. So, if I were to split the polyphase components in the following fashion, I am going to introduce a very specific notation, please note that, and then we will just. So, these filters f naught of z, I want to do again, because eventually I want synthesis filter bank requires delays. So, I am going to use type 1 polyphase decomposition. So, type 1 polyphase decomposition says summation k equal to 0 to n minus 1. Notice it is now already in terms of n, no longer m, and it will be z power minus k g k m z power n. Okay. Now, two indices are there. Basically, let me just do this, fm of z, where m can be 0, 1 through m minus 1. Okay. That is the filter index. The second one represents the filter index. So, the filter index is, say I am talking about f0 or f1 or f2 or fm minus 1. So, that is the filter index, and the second one is the polyphase component index. So, polyphase component index, the polyphase component index will go up to n minus 1, polyphase component index. Okay. So, the range of k is from 0 to n minus 1, the range of m is between 0 to m minus 1. Okay. So, now if I were to write this, write the expression for this, please help me with it, just verify that you have the correct expression. So, I want to write down an expression for f naught of z, f1 of z, fm minus 1 of z. This can be written as a row vector 1 z inverse z minus 2 z power minus n minus 1. Notice this is n minus 1. So, the one on the left hand side is a 1 cross m vector. Okay. This is a 1 cross n vector. Okay. The next part of this are the polyphase components. All the polyphase components of f0 must be along the first column, because only then they will get combined by the delay chain. So, this will be g00 of z power n, g10 of z power n dot 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 g m minus 1 comma 0 of z power n. Not m minus 1, there are n minus 1 polyphase components. So, it should be n minus 1. Okay. Okay. So, these are the polyphase components of F0. If you go back and verify, that is the representation that we have given. Okay, did I write? Yeah, GK polyphase component is the first one, the filter index is the second one. So, the second index is all 0, that represents F0. The second, we will just write one more column and then we will finish with that. This will be G0 comma 1 of z power n all the way to Gn minus 1 comma 1 of z power n, and the last column will be G0 comma m minus 1, that corresponds to the m minus f of m minus 1, okay, and the second term will be G of 1 comma m minus 1 z power n, and the last one will be G of n minus 1 comma m minus 1 z raised to the power n. Those are the polyphase components of the filter f m minus 1. Okay. Number of columns is m, number of rows is n. So, therefore, 1 cross n into n cross m gives me a 1 cross m, everything is dimensionally consistent. But how are we going to represent this? Very important. In our course, we are going to indicate redundancy in the following way. Again, it is a very interesting, a very compact and a pictorial representation. S0 of n is the first entry, second input the m minus 1th input. So, this is S1 of n, Sm minus 1 of n. Each of these will be upsampled by a factor of n, This is where the redundancy is coming in. Okay. Now, this is going to be filtered through the polyphase component matrix. Notice how I am drawing the polyphase component matrix, m inputs, n outputs. So, it is a trapezoid, not a square matrix, because that basically shows the growth in the signal representation. This is where the redundancy part is coming in. I went in with m signals, I come out with n signals. So, basically this is a n cross m matrix, and that is exactly what we have represented here. So, this is nothing but G of z n, the matrix, and it is nothing but the matrix that we have written down here. Now, how will these signals be combined? These outputs are combined through a delay chain. So, basically this is a summing node. I have a delay chain here, another delay chain, another delay element, and so on until we have the last delay element. So, let me number the delay elements. This is delay element number 1, this is delay element number 2, this is delay element number n minus 1. Remember, there are n branches coming out. So, there are m going in. So, this is 0, 1, number 0, number 1, number m minus 1 going in. I have number 0, number 1 and number n minus 1 coming out, and I am combining it through a delay chain, and this is a representation, polyphase representation of a multi-carrier system. We have not yet built the full system, we have only built the transmit portion of it, where we said that we are going to do upsampling by a factor of n, we are going to introduce some redundancy, and then we are going to see if we can exploit it in the in a way that is advantageous to us. Okay. Now, very important question, can I apply noble identity here? if every entry of your matrix is a function of z power n, yes, of course I can apply, which is the case. So, if I apply the Noble identity, what is the structure that I get? So, basically it will be the m inputs S0 of n all the way to Sm minus 1 of n. Now, it is still a trapezoid, but it is a function of z, g of z. Basically all these polynomials that were g of z power n have become g of z, and on the right hand side we have the upsamplers, upsampling by a factor of n, upsampling by a factor of n dot dot dot, upsampling by a factor of n being combined through a delay chain of n units. Okay. Indicate the arrows so that there is no confusion. So, basically we have achieved a very similar structure to the synthesis filter bank with the polyphase representation, except that 5 minutes, except that we now have the it is now a system where redundancy has been introduced. Okay. I hope the aspects of redundancy you can kind of see it coming in. Redundancy incorporated. Now, how exactly we are going to exploit this incorporated? How exactly we are going to leverage this? That is what we are going to be studying. Incorporated above. Okay, so that is where we are in terms of this this aspect. Now, let us develop it a little bit more in terms of the mathematical representation. I would like you to, because as you know, just like we are building the process up, this is also very important for us. Now, if you go back to the synthesis filter bank, the synthesis filter bank basically says that I am upsampling by a factor of n, filtering by f naught, correct? Okay. Can you tell me how to write down the expression if I call this as u naught of n, u naught of n? Can you tell me how to write down that expression? Basically u naught of n can be written as summation over j f naught of summation over j, okay. Let me see if I am making this, writing this correctly. Yes, summation over j s naught of j please check if I writing it correctly, s naught of j times f naught of n minus j n, correct? We wrote down that we would write down the we could write it down in this fashion. Okay. Now, if the combined signal is labeled as x of n, can you write down a mathematical expression for x of n? X of n is equal to summation k equal to 0 through n minus 1 of uk of n, which means it will be summation k equal to 0 to n minus 1. Am I correct? No, there are only m minus 1. Always have to check that, because this redundancy part is just have to be careful with writing the. So, this is m minus 1 and this is also m minus 1. Okay. Summation k equal to 0 to m minus 1 of uk of n. Each of those UKs are a summation over j sk of n sk of j, sk of j f k of n minus j times n. Okay, just make sure that we got it correct. So, this is a place where we can see that the different subcarriers are mixing, okay, because this x of n is actually a multicarrier signal. So, this is where the subcarrier are mixing, all the or in other words the sub channels are mixing. So, we have to design our carriers in such a way that these mixing parts are taken care of correctly, and then we are able to recover the signal in a very effective manner. Okay. So, any questions on what we have done as far as the redundancy? We kind of sowed the seeds for the notion of redundancy. Redundancy means that you have to use some additional resources. The additional resources that we are going to use is in the form of additional bandwidth. Additional bandwidth means your sampling rate has changed. So, that means your sampling rate is a bit higher. So, therefore, upsampling by n and not by n. Now, if I want to get efficient polyphase implementations, I must do the polyphase decomposition and apply the noble identities. So, now I need to split it into n polyphase components, though I have only m filters. So, again this is the way in which we have developed the notion of redundancy and how we want to move it forward. Okay. Now, let me just add one more element, and then we will conclude this section and take a short break. So, I hope this representation using the trapezoid is comfortable. Then the application of the polyphase component is also. So, now I want to move to the analysis filter bank. Okay, analysis filter bank is the one where we are going to split it back. Analysis filter bank. If you remember, the analysis filter bank is where you do the serial to parallel conversion. There we wanted to have it as powers of z. So, here is the representation. I will just introduce it and then we will pick it up in a few minutes. So, if the filters that I have in my analysis bank, if I call them as the filters are H, if I denote them by H. So, here is a way to visualize it. H m prime of Z, I am writing it as type 2 polyphase components, k equal to 0 to m minus to n minus 1. Again, remember we are its redundancy has been introduced to n minus 1, z power minus n minus 1 minus k, this is type 2 polyphase decomposition. I am going to use the polyphase components SMK. Okay. Notice that there is a swapping of the index notation. The first index represents the filter index, the second one denotes the polyphase component index, because this matrix is going to appear in a transposed form with respect to the other one. So, polyphase component index. Okay. Now, this should be function of Zn. Okay. Now, again factor out z power n minus 1, z power n minus 1 times h m prime of z can be written as summation k equal to 0 to n minus 1 z power k s m k of z power n. I am going to call this as my filter h m of z just for ease, basically it is just a shifted version of it, and I will now derive the implementation of the analysis filter bank, implement the analysis filter bank with the filters h naught of z, h1 of z dot to h m minus 1 of z. Okay. Now, remember this is a type 2 polyphase decomposition, and I want to characterize this. So here is the polyphase implementation that we will achieve with this, and basically now we would then put the two pieces together to get the complete multi-carrier system. So the part that we want to build in here is how do I implement the this particular filter. So the analysis filter bank takes the common signal and then passes it through the filters and then splits it up. So here is the visualization of the analysis filter bank. This is the one that splits it back to the sub signals. I will take x of n, whatever is coming on the channel, pass it through a filter h naught of z, and I must downsample it. In the original case I would have done it by m, now I have to downsample by a factor of n, and this signal now becomes x naught of n. Okay. Now I have to do this for all the filters. H1 of z downsampled by a factor of n, this is x1 of n dot dot dot. The last branch is m minus 1, h m minus 1 of z, that is the last filter, again downsampling by a factor of n to obtain x of m minus 1 of n. Okay. Now write down the matrix expression that we have done, and we should be able to show the following implementation. Again I will pick it up from here after the break. So basically write down the polyphase component matrix, apply the Noble identity, you should get downsample by n, an advance operator z, downsample by a factor of n dot dot dot. You have n such parallel branches, the last one is followed advance operator followed by downsample by n. So there are n branches coming out. We will let's label them as x naught hat of n, just to show you how many signals are there. X1 hat of n, n minus 1 hat of n. Okay. Now the filtering part, the polyphase filtering part, it is a trapezoid, but it input more number of inputs, fewer number of outputs. So I denoted by a trapezoid in the other direction. So call this as S of Z matrix, polyphase component matrix. We will write down the structure subsequently. This then producing m outputs that we are interested in, which should be the signals of interest x naught of n, x1 of n, x m minus 1 of n. Okay. So what we have done is whatever we did for the synthesis filter bank, we have been able to do something very similar, except that type is now type 2 polyphase decomposition, so that you get a string of advance operators and not delay operators, and you have done the moving the downsampler to the extreme left, so that you can apply an implementation, efficient implementation. This matrix S of Z is not a square matrix, it is a rectangular matrix. The dimensions of S are m cross n. So it takes in n inputs, produces m outputs, so therefore we have shown it as a trapezoid and we have this representation. Okay. So if I were to say it in words, what did we do here? We blocked it into the we did a blocking operation. If you remember, this is called a blocking operation. Okay, so the first step is a blocking operation. Blocking operation is also another name for parallel to serial to parallel conversion. So, this is the same as serial to parallel conversion of dimension n. Okay, so that is exactly what is happening there, serial to parallel conversion. That is first operation. Second operation, it was filtered by a MIMO system, multiple input, multiple output. This S of Z can be treated as a MIMO system. It takes in some number of inputs. So, it was these signals that were obtained through the blocking operation by a MIMO system. The dimensions of the MIMO system are m cross n. It is a MIMO system. Okay. Once you finish the filtering by the MIMO system, then we look at the output. The output has produced m outputs. Okay. The similar thing you can write down for the synthesis step. There what would you have done? You took m inputs, you filtered it through a MIMO system which expanded your signal representation, and then you did a parallel to serial conversion and fed it into the channel. Okay. So, that is the counterpart of this. So, this is what we have developed so far, but with this framework you can achieve some amazing insights and actually completely develop the multi-carrier system in a multi-rate framework, multi-rate DSP framework. That is what we will do in the next session. Thank you.